Hello friends, we're going to talk about Module 10, rational functions. So when we're dealing with a rational function is a ratio of two polynomials. So we've already talked about polynomials in Module 9. This is a polynomial over a polynomial. And then, of course, we have to say Q is not 0 because we're not allowed to have 0 in the denominator. So here we just have two pictures of some basic, or we could consider them as parent rational functions. So before we get into all the rules, I'm going to work through an example with you. All right, so this is an example of a rational function. We have a quadratic polynomial over another quadratic polynomial. And of course, looking at these, both of these, the numerator and the denominator, can be factored. And then one other thing to notice is that we have this pair of factors here that's going to reduce out. So if I take that and reduce it away, I end up with just x minus 1 over x minus 3. So we have a couple of rules for talking about horizontal asymptote. A horizontal asymptote is determined by what we call the comparison test. And we'll go into that in a second. But our comparison test, basically we're going to look at the degree of the numerator and then also the degree of the denominator. So in this case, n is 2 and d is 2. And what we can say is if n equals d, then we're going to have y equals a over b. And when I say a over b, a and b are going to represent those leading coefficients. And that number in front of each of those, if you look right here, I drew a little invisible 1. Okay? So in this case, we're going to end up with y equals 1. And you can see y equals 1 is showing up right here on my graph. Okay, well, domain isn't new to us. The domain are the values that make the denominator 0. And it's easy for us to see in this case that positive 3 and positive 5 would make that denominator 0. So in this case, we know that x can't be 3 or 5. And in interval notation, the way we would write that would be that x is from negative infinity to 3 union 3 to 5 union 5 to positive infinity. So again, those values are coming from these two factors in the denominator, and we are looking to determine what would make them 0, so we can leave those numbers out. Wholes. If we think about the whole, that's going to come from the canceled factor. So if you look up here, that minus 5 factor is going to cancel. And that means we know there's a whole at x equals positive 5. And I can't plug 5 straight back into my original problem, because if I put 5 in here or I put 5 right here, I'm going to get 0 in the denominator. So I'm going to plug 5 into my reduced version. And so doing that, f of 5 is 5 minus 1 over 5 minus 3, which gives me 4 over 2, or 2. And we can see that there's a whole at 5, 2, right there. Okay, so because that 5 canceled, that ended up being what we, where the whole occurs. So the function has one factor left in the denominator, and that factor is x minus 3. So my vertical asymptote we can see is occurring here at x equals 3. That is the leftover factor. All right, now vertical asymptote is a vertical line, so we're going to write that as an equation. The x-intercept is coming from what we have left over in the numerator. So the x-intercept is going to be at 1, 0. And then the y-intercept, we've been talking about y-intercepts all semester. Y-intercepts can be found by letting x equal 0. If we let x equal 0 and we plug that in, we're going to get out 1/3. All right? So moving on to the next page in our note, we have all of our steps for how to do this. The first thing here, horizontal asymptote, we use what we call the comparison test, which is what I said on the last page. And what we're going to do is we're going to compare the leading term in the numerator and the denominator. And we're going to look specifically at the degree. And we're going to compare those two things. Either n is less than m, equal to m, or greater than m. If it's less, we're going to end up with y equals 0. If it's greater, we end up with y equals a over b. And a and b are these leading coefficients. So we're looking at both the degree, the n and the m are the degrees, and then the leading coefficients a and b. And then if the numerator has a greater degree than the denominator, there is no horizontal asymptote. We have what we call an oblique asymptote. Okay? You may cross a horizontal asymptote. Domain should not be new to us. We've been talking about domain all semester. If we think about domain, we just need to make sure we know that the denominator can't be 0. Those are the values that we need to exclude. And anything we're excluding is going to represent a whole or a vertical asymptote. Wholes, we talked about this on the last example, are very important. They're common, reducible factors. So things that you can cross out. They're going to occur in both the top and the bottom, the numerator and the denominator. In order to find the whole, set each common reducible factor equal to 0, find, and then you're going to plug it into the reduced version. Again, we'll do another example. Vertical lines, that's going to be any factor that is left in the denominator. So generally, not always, but generally you're not going to have a whole that is also a vertical asymptote. Okay? So whatever crosses out is going to represent your whole, and whatever is left in the denominator, that is going to be your vertical asymptote. One thing to remember about a vertical asymptote is that you cannot cross a vertical asymptote. When we write a vertical asymptote, we need to make sure we're writing that as a vertical line. So whatever is irreducible or left in the denominator, that's what you're going to set equal to 0 and use that to solve. And then finally here, x-intercepts and y-intercepts, those aren't new. The x-intercepts come from setting the function equal to 0 when it's in its most reduced form. And then the y-intercept comes from letting x equal 0. So x-intercepts are let y equal 0. Y-intercepts, we let x equal 0. And then we take all of that together and we graph it. And of course, you're going to have your graphing calculator, so you can use that to check. So on to example 2. Here we have a rational function. It's represented by a quadratic polynomial divided by another quadratic polynomial. So when we're dealing with rational functions, we always want to make sure that we factor and reduce as possible first. In this case, my numerator factors, and I end up with 2. X minus 3, x plus 1 over x minus 1, x plus 1. And so you can see that we're going to have something that reduces, and we'll think about that when we get there later, but my rational function is going to turn into 2 x minus 3 over x minus 1. So we'll go ahead and look at the horizontal asymptote first. The horizontal asymptote, we find that by considering the comparison test. And the main thing we want to think about is that leading coefficient over the leading coefficient. And we can look at it in either form, the original form or the reduced form, which you see here. But it's always easy to go back to that original form. And keep in mind that this guy and this guy mean exactly the same thing. It's just that this one over on the right has been reduced, so part of it is missing. But we'll look at this. So the numerator and the denominator, I've got 2x squared over x squared. The numerator is 2 and the denominator is degree 2. And since they're equal, that lets me say, well, that means y equals a over b. And a and b are the ratio of my leading coefficients. So in this case, y equals 2 over 1, or just 2. All right, now the domain, those are any values that the function's not allowed to equal. And in this case, the function can't equal, looking at our denominator here, there are two numbers that we would have to leave out. X can't equal positive 1 or negative 1. So if we wanted to write that in interval notation, we would say negative infinity to negative 1, union negative 1 to positive 1, union 1 to infinity. All right, moving on to the whole. The whole occurred because we canceled x plus 1. So when we canceled x plus 1, if we set x plus 1 equal to 0, that would let me know that we'd be dealing with x equals negative 1. So there's a whole at x equals negative 1. And in order to find that value, I'm going to plug the negative 1 into my reduced version. All right, I can't plug it into the original version because I'll get 0 in the denominator. So I'm going to take this x equals negative 1, and I'm going to plug it into the reduced version, and that is f of negative 1 equals 2 negative 1 minus 3 over negative 1 minus 1. And I end up simplifying that down. It becomes 4. So the whole is at negative 1, 4. The vertical asymptote is going to come from what we have left in the denominator, the factor that didn't cancel. So if we're thinking about the vertical asymptote, we're thinking about these two pieces, these two factors that didn't cancel. So I've got negative x minus 1 and x minus 1. If I were to set each of those equal to 0, I'm going to end up with x equals positive 1. All right? The x-intercept, we've been doing those all semester, but that comes from setting the function equal to 0. We can go back to our reduced version. I'm going to see that 3 is where my x-intercept is going to occur. So I'm going to have an x-intercept of 3, 0, and my y-intercept is going to occur by plugging 0 into the function. F of 0 is going to leave me with returning a 6 as my output. And I can plug that in, the 0 in up here. I can plug the 0 in to the original function. So reduced or original, both works. And what you'll notice is if you consider the ratio of those constants, negative 6 over negative 1, we're getting that output of positive 6, right? So it's always going to be the ratio of the constant terms, just like it is the constant term in a linear or quadratic polynomial. So my y-intercept is the ordered pair 0, 6. So I've got 0, 6 for my y-intercept, 3, 0 for my x-intercept, a vertical line, x equals -1 for my vertical asymptote, a hole at -1, 4. My domain in interval notation basically states that x can't be positive or -1. And then we have a horizontal asymptote here. The horizontal asymptote is y equals 2, and that came from the comparison test. So if we think about graphing this, we're going to draw our horizontal asymptote here first at y equals 2, and my vertical asymptote at x equals -1. So these are imaginary boundaries that the graph is going to approach but never touch. The hole can be plotted at -1, 4, so I'll draw that as an open circle on my graph. I have an x-intercept at 3, 0, 1, 2, 3, and a y-intercept at +6. All right, so I have a couple of points on my graph. Now, at this point, you as a student could go and type this into your graphing calculator. I can't pull that up here on my iPad, but you should be able to view something that looks roughly like this rational function on your calculator. Remember, you can always hit zoom 6 to choose the correct window. All right, that'll put you on a standard window.